Okay, so for this video, I'm going to try to explain just how iron is regulated in the body, iron levels. I'll do my best. I don't have a complete understanding of it, but I'll see what I can do. So in the blood, basically you have the transferrin protein. And what it does is it transports iron within the blood. And then in the cells, you have ferritin, right? And so ferritin sequesters iron so that it doesn't cause any damage to the cells. And so if you draw, this is intestinal cells, so these are endothelial intestinal cells, and basically iron will be uptaken into them. This is the blood vessel. So iron will be uptaken into the endothelial cells, and when iron is low, basically these cells will have a ferroportin molecule on them. So ferroportin's there. And ferroportin allows iron to be transported to transferrin, where it can then go to these cells. And these cells have transferrin receptor 1s on them that bind transferrin and allow it to transfer to ferritin within the cells. And so what you'll see is when somebody is deficient in iron, is transferrin will be really high. There'll be a lot of ferroportins on the cell, and so because the body will want to uptake the iron and be transporting it. But you'll see in the cells that they'll have quite low levels of ferritin because there won't be that much iron to store within the cells. The opposite is true when there is low levels of iron, or high levels of iron. When there's high levels of iron, you won't see that many ferroportin molecules on the cells. Transferrin levels will be low in the blood, and ferritin will actually be very high, and that's basically to sequester all the iron so that the iron doesn't cause any damage to cells, because that's a toxic chemical. Okay, so how is ferroportin regulated? So in the liver, you have hepatocytes that basically what they do is they have receptors on them, which are known as transferrin receptor 2 molecules. And so what these do is these actually measure, you can still see that, yeah, on the video. These measure the saturation of transferrin. And so when transferrin is really saturated, this receptor will be activated, and what it does is it activates the gene HFE, and HFE is actually upstream of the real protein of interest, which is hepcidin. And so when transferrin saturation is high, hepcidin will be transcribed. What it does is it then binds to ferroportin, and ferroportin is then brought into the endothelial cells where it can then be degraded. So when you have iron overload, basically you won't see any ferroportins on these membranes because of the regulation of hepcidin. So then what will happen is if there's iron overload, basically these cells are continually shed. They're shed approximately every 2 to 6 days is their lifespan. And so what you'll see is you'll slowly get rid of iron that way. And so that's actually, iron overload is a very toxic effect, just because this is the only way that the body can rid itself of iron is through stool. It doesn't go out through urine, sweat. If you're a female, menstruation is also another way of getting rid of iron. So iron absorption makes up approximately 1 milligram a day of iron is absorbed, and approximately 1 milligram is shed. And then the rest of it is actually recycled. So approximately 19 milligrams of iron is recycled. So the hemoglobin is recycled. So when red blood cells, when they reach approximately 100 days, they will be absorbed by reticuloendothelial phagocytes. Okay, these will take in them and actually absorb the iron. And these cells also have ferroportin on them, which can transport it to transferins. So, what conditions actually regulate hepcidin? When will you see hepcidin transcribed? So you'll see that when iron overload occurs. So if there's an increase in iron in the liver, basically hepcidin will be transcribed to prevent more iron uptake. You'll also see it during acute inflammation events, and that's actually regulated by cytokines. So when there's a release of cytokines, it will increase hepcidin. And my reasoning behind this is like during infection or something, there'll be a lot of red blood cells that could be getting damaged from the inflammation. And so this iron will be getting uptake by the phagocytes. You don't want this iron being released. It's highly toxic, right? You want it contained. And you also don't want the infectious pathogens from getting at the iron. So you want it contained within these cells. And for that reason, you increase hepcidin to prevent it from being transported by the ferroportin molecule. And the last one where you'll see hepcidin actually increased is when there's high ferritin or high transferrin saturation. Okay, when is hepcidin decreased? So hepcidin's decreased in cases of hypoxia or anemia. So during hypoxia or anemia, basically the body knows that it needs to produce more red blood cells, and it'll decrease the transcription of hepcidin, which allows for more absorption of iron, and thus what you can often see with anemia is even if it's producing red blood cells, but they're ineffective, so there's still a hypoxic environment, you can actually get iron overload in these cases. So anemia doesn't just have to be caused by iron deficiencies. You'll also see hepcidin decreased during hereditary hemochromatosis. So during hereditary hemochromatosis, basically this is hereditary, right? And it's caused by excess iron overload. And basically there's usually like a mutation in the hepcidin molecule so that it's not, there's a deletion or something so that it's not actually transcribed. And so there's no regulation of iron uptake. And the last one that I've kind of mentioned is ineffective erythropoiesis. So even though you are producing red blood cells, so it's not technically an anemia. It's not like you have low red blood cell count, but because it's still in a hypoxic environment, you'll see low hepcidin.